about planet Saturn. Alright, welcome to the planet Saturn video. We're going to start by looking at the semi-major axis. I think we already know how we find the semi-major axis from our previous videos. So we have our aphelion, which is the A, and the perihelion, which is the P, yellow and blue respectively. And our semi-major axis, according to that white knot that we see in most of our videos, it says let us make Z the semi-major axis, which is the semi-diameter, which is the last sentence there. So our Z will be equal to A plus P over 2. That will then be 10.1238 plus 9.0412 over 2. And that will give us 9.5825, which is approximately equal to 9.58 astronomical units. Okay, now I want to convert to meters, because we're not given meters where we have the aphelion and the perihelion there. We just have astronomical units. So I want to find the semi-major axis in meters, but without using the actual values of the aphelion and the perihelion in meters. So our conversion rate will be 1 meter is equal to 6.685 times 10 to the power negative 12 astronomical units. That's equal to 1 meter there. So what we do is we divide the 9.5825 divided by that value in astronomical units for 1 meter. So we get the number of meters, the meters for the semi-major axis, which is equal to 1.4334 times 10 to the power 12 meters. Then we find that that value is very big. We might need to put it in kilometers. Usually we put it in kilometers just to scale down the value. So we have Z in kilometers. Our Z is the semi-major axis, so we're basically saying the Z subscript kilometers is basically semi-major axis in kilometers. That's what we mean, which is that value for the semi-major axis in kilometers divided by 1000 meters, because there are 1000 meters in a kilometer, which is equal to 1433 million kilometers, correct to 4 significant figures, or you can say 1430 million kilometers, correct to 3 significant figures. Okay, now I want to calculate the orbital speed. It should be the Mars video. I think we'll put the link somewhere so that you can visit the video where we explained how to derive that expression v bar is equal to the square root of gm over the semi-major axis. So we know the first equations, the parent equations for that expression are the gravitational force and the accelerating force, which is the centripetal force, where the planet will be accelerating as it is going around the sun, as it is orbiting the sun. That would be the centripetal force. Centripetal because that oval shape is close to a circular shape. We know the centricity is not as big as you are seeing it in that diagram. It's actually very close to a circular shape, probably less than 0.2. So that you may need to adjust if you are confused. That's not the actual diagram for the orbit or the ellipse of planet Saturn. So in Mars we explained that the derivation of that expression v bar is equal to the square root of gm over z using those two formulas for the forces. Basically you're assuming that the centripetal force is equal to the force of gravitation for us to be able to find that average speed, because we're trying to find the average. So we assume that at the average speed both forces will be equal. So if we plug in our values into that formula, we find that our g will be the gravitational constant, which is equal to 6.674 times 10 to the power negative 11, multiplied by the mass. There's the mass there, which is the mass of the sun. That's the larger mass, which is 1.989 times 10 to the power 30 kgs. And that will be over the semi-major axis, which we now know. and then we square root that value, and then we get 9624.7043, pardon me, 44 something going forward, meters per second. That's another way of writing meters per second, or you can say m backslash s. That's also another way of expressing meters per second. And then we divide that value by 1000 so that we get our kilometers per second. We're trying to work with smaller values, which will be equal to, our v bar would then be equal to 9.62 kilometers per second. Yeah, that's another way of writing the per second. Instead of saying s to the power -1, you can just say backslash s. That will be correct through to 3 significant figures, and I think that's basically it for you to understand. If you are a bit confused, maybe you might need to refer to the Mars video where I explained everything very clearly. Okay, now we move on to we're going to be working with the orbital period for now, but I think we already know how to derive these formulas or expressions for the same age axis and the orbital period. We've covered that in previous videos. If you may need to watch those videos and understand the Venus video, the Mercury video, I think the Make as well, you can watch those videos and get a better understanding of how to derive those equations. But that's basically how we derive those equations using Kepler's third law. So we are going to be concentrating on the orbital period, as we can see. So according to Kepler's third law, which states the square of the orbital periods of the planets are directly proportional to the cubes of the semi-major axis of their orbits. So Saturn's orbital period is therefore, the orbital period will be in Earth years. We want to find it in Earth years. We found that our expression will be t is equal to 2 pi. I think you can understand where the 2 pi is coming from. It's the orbit, which is almost a circular shape. That's 2 pi in radians. That multiplied by the square root of the cube of the same major axis over the gravitational constant, the product of the gravitational constant and the mass of the sun. And you find those values are plugged in there. We looked at those values before, and then we get our value for the period in seconds, which is 935,488,948.4 seconds. Now to convert to years, we have to divide that value by 60 seconds, right? So that we convert it to minutes. Then we divide by 60 minutes again. That's why we're having to multiply all those values in the denominator. We're basically skipping steps. I have just put all of the values and multiply them together, so that we just get one value to divide into that to save on space. But you can do it step by step. You first divide by 60 seconds, then you get your minutes, you divide by 60 minutes, you get your hours, you divide by 24 hours, you get your days, and then you divide by 365 days, which are in a year, in order for you to then get the years. And then when you divide all those values into that value, you then get approximately, I think, 29.6 something. That's the value we got. That will be approximately equal to 30 years, as you can see. But other sources, if you check with Wikipedia, I think in NASA and the like, they have 29 years as their value. If you find an error in the calculations, please just share with everyone in the comment section so that we can see where I went wrong. It's possible I can make mistakes, but it's good for us to correct each other in the comment section so that I see where I made an error. But it's probably a minor error because the values are so close to each other, and we can approximate them to 30 years. But nonetheless, that's basically how we calculate the period in Earth years. These are Earth years. We have what we call light years as well, but that's for another day. Right now we are concentrating on Earth years, something that we can relate with on this planet, on Earth, in our world, and what we study. So basically we are trying to say, whilst Earth is making one rotation, which is 1 year, around the sun, planet Saturn will be taking around 30 or 29 times the years of Earth to go around the sun. So Earth just goes once, but the period that Earth goes around the sun once, multiplied by 30 or by 29, that's the period in which Saturn, the planet Saturn, goes around the sun. Quite fascinating, but yeah, it also deals with the distance. I think we looked at the relationship of the Kepler's law graphically with that line graph, the log-to-log plot of those planets and their periods compared to their same age axis in our, I think it should be the Venus video, if I'm not mistaken. I'll put the link there so you can see the graph. If you look at that graph, you can see that the further you go away from the sun, somehow the period becomes greater as well. That's why Earth takes a shorter time to go around the sun than planet Saturn, as we can see in our values. But yeah, I think that's basically what we have now. Try to make the video short for you, just so that you can at least enjoy. I know many people don't like calculations, but I think it's best if we can appreciate where these values come from. It's very simple mathematics, very simple physics, very simple mechanics. I don't think there's nothing hard. It helps us to understand this is the language of the universe, as Dr. Neil deGrasse Tyson always says. It's the language of the universe. Mathematics is the language of the universe. So it's best we understand these things in our universe using the language, so that we can have a better appreciation of what happens in our universe. As for me and for the video, I think, or the calculation segment, I think we're done. Enjoy the rest of the video as you explore more about this beautiful planet with the dim halo. This planet called Planet Saturn. Cheers to Planet Saturn and beyond. We'll meet next time. More on this gas giant. Cronian rings.